And the next speaker that we'll have will be Alaa Taha presenting AutoAFIDs, BIDS app for landmark detection, QC, stereotactic targeting, and brain charting. Thank you very much.
Well, thank you for the introduction. I have no disclosures. I want to start out with a quick overview of the work that I'll be presenting today, which is going to revolve around brain coordinates or brain landmarks. Our lab has taken an interest in standardizing the way we place landmarks in the human brain and ascertaining that we've placed these landmarks, whether for surgical targeting or brain mapping, with millimetric accuracy. And so the goal that I'm going to be presenting today is going to leverage this infrastructure to build a deep learning model that allows for the automatic localization of brain landmarks with a high degree of accuracy. And I'm going to talk about 3 applications of this automated landmark localization. So I want to start out with some foundation. So a few years ago, we published the AFIDs protocol, which is a protocol that describes the location of 32 anatomical landmarks that survey various regions in the human brain. You see on the right-hand side of my slide an animation that pans through the 32 AFIDs that we've released. We've employed the AFIDs protocol in various local brain hacks where we asked trainees of varying expertise to annotate the AFIDs protocol. And what we found is that most of them are able to place this or complete this protocol with an accuracy within 2 millimeters. And so we released this data with the neuroimaging community. And on the left-hand side of my slide, you see a rotating 3D chart where each point on that chart is a ground truth annotation for a particular subject that's curated by at least three human raters. And so we curate this data set across a wide variety of MRI field strengths and health and disease. And so I want to talk a little bit about building AutoAFIDs. So we performed a stratified split of our data for machine learning. We pre-processed our structural MRI scans with typical pre-processing, pre-machine learning. And we built our machine learning using a unit architecture. We built 2 BIDS apps. The first is a training BIDS app, and the other is a BIDS app for inference. What this means is if your data set is in BIDS and you have some coordinate data, you can essentially train your use our framework to train and do inference on your data. We expose various TensorFlow and Keras elements at the command line interface, and all of this is accessible on our GitHub repo as part of the larger AFIDs ecosystem. So I want to report the accuracy of AutoAFIDs on the 32 landmarks across our testing set. So we report a median accuracy of 1.2 millimeters. We were able to localize the midline, or AFIDs that lie on the midline with sub-millimetric accuracy, and then AFIDs that lie laterally with millimetric accuracy ranging between 1 to 2.4 millimeters. And on the right-hand side, you see an MNI plot with where these 32 landmarks are and how well we've localized them. Now you're probably wondering, how does this compare to human raters? And so we did a statistical comparison between inter-rater error and AutoAFIDs, and we found that for the majority of these 32 landmarks, AutoAFIDs performs just as well as human raters. And so I want to dive into the applications of AutoAFIDs now, and the first is in image registration. So this is a typical image manipulation where you move your native scans to a stereotactic space or the MNI space. And most of the tools that do this automatically resort to region of interest. What we're proposing here is to use these landmarks that are automatically generated by AutoAFIDs to quality control this registration. So rather than using voxel overlap, we're proposing a millimetric and interpretable error. So we did a head-to-head comparison between what voxel overlap might allow you to see in terms of registration error and what our AFID-derived registration error, which you see there on the y-axis. So the first comment I want to make about that comparison is that you notice that the dynamic range of the registration error is much more generous. And the other is that once you get to above 3 millimeters in terms of error, there are misregistrations that we're capturing with our AFID framework that we're not necessarily capturing with a metric like digicard index. So the other aspect of many tools that perform quality control for registration is that they provide qualitative metrics. There's nothing wrong with qualitative metrics, but we thought adding some millimetric component to these errors is hopefully going to close the gap, and I'm going to show you a little bit about why that's important later. But this is what AutoAFIDs would generate if you provided a FMRI prep or a lead DBS directory, where we provide a balance between the qualitative quality control and a summary of quantitative errors. And then you can see this in 3D space, where we can represent the errors in registration as vectors between the 32 landmarks that we propose within the AFIDs framework. So why is this important generally? What we did in this analysis is move all of our subjects to MNI space using fMRI prep. And if we zoom in at some of our landmarks of interest, you can see that certain data sets, so each point in this plot represents a participant that has been moved to MNI space. And then these data sets are clustering differently based on the composition, the cohort composition and field strength of that data. We can probe that more directly with a PCA of the errors. Essentially what we're seeing here is that there are different error profiles that arise in MNI space because of these variables. And so we're hoping to close that gap with providing more quantitative metrics for registration. The second application I want to talk about today is in stereotacti. So you see on the right-hand side of my slide a patient with a deep brain stimulation on and off. Now millimetric targeting in DBS is the difference between optimal treatment and side effects. And so when we look at the most common target for DBS, which is the subthalamic nucleus, typical literature reports an inter-rater error of 1.9 millimeters. We were able to bring that down to 1.2 millimeters with our AFID-based framework. And the takeaway message from this is that we're able to generalize this across field strength. So we can use we made use of a paired data set where we investigated our accuracy, and we showed that we're fairly consistent across field strength in predicting the SDM. So the last application for today is in brain charting. So if you were to plot the pairwise distances between all of the 32 landmarks within the AFIDs protocol, you end up with a 496 pairwise distance matrix. We applied this matrix automatically on 9 public data sets, as you see on the right-hand side of my slide. And we did a PCA on a global pairwise error. So we found a strong clustering based on biological sex when we did PCA, when we plotted the first principal components. We found an interesting gradient with age, and moderate clustering with disease relative to healthy controls. And here the 3 populations are Parkinson's disease, Alzheimer's disease, and healthy controls. And a fairly heterogeneous clustering with regards to the data set that was used. We also looked at the correlations of these pairwise distances with age. And so what you see here is the top 20 highest correlated pairwise distances, which we found to be more in the periventricular areas and span the left and right axis of the brain. The highest negatively correlated distances with age were mostly in the subcortical areas and span the anterior-posterior direction. And so here's a plot that shows these distances and the correlations with age. We can also probe these distances in a more localized way. So we looked at the anterior and posterior commissure line, which is typically used in neurosurgical or stereotactic planning. And what we found is that this distance increases with age, with it being longer in males compared to females. And when we did an age and sex matched comparison with Parkinson's disease, we found that Parkinson's disease features longer ACPC distances. And so with that, we package AutoAFIDs as a BIDS app that's trained on T1 weighted images, but we support other modalities using SynthSR. All of the applications I talked about are available as flags within the typical BIDS app syntax. We provide various modes of installation on Conda and containers. And I'd like to invite you to my poster, 1839, to maybe have a more detailed discussion. So with that, I want to acknowledge the support of my lab mates, supervisors, sources of funding that made this work possible, and I'm happy to take some questions.
Thank you you so much, Alaa. I don't see any questions in the app for our speaker. Anyone wants to get to the microphone? Otherwise, it's great to see that you've been able, among many other things, to leverage the community through the Brain Hacks events. I think this is a fantastic demonstration of how useful these events are. Maybe my question is a question I could ask to everyone. What was the greatest challenge from your perspective to put this together?
Yeah, that's a tough question to answer. I think it depends on what aspect of the project we're talking about, because there's a lot of things that I presented today, partly about the data release, for example. We got open data sets from all sorts of centers, and so harmonizing these data sets into an easy to download, maybe data lab structure was difficult. From a machine learning perspective, the difficult piece was figuring out what is the best model and how we can package that model so that it's easy to use. Yeah. So there's a lot of challenges, but yeah, I mean, I'm glad to be able to present this work here. Yeah.
Congratulations, indeed.
Thank you.
Thank you.